Swayam Prabha. Digital India. Educated India.
Welcome to the subject on advanced digital image processing and computer vision. We are discussing about image transforms, and in the last lecture we started with wavelets. So let us continue from that point. So the basic motivation of using wavelets for getting an image transform, which means an alternative description as I mentioned earlier, is that wavelets, the basis function of the wavelets should be in such a way that it should not only localize the domain characteristics, original domain, for example, time or space of the signal, they localize that points of the signal, and also it shows what is its effect in the transform domain. So just to explain that part, let me consider any particular signal, say any arbitrary time varying signal. Say consider this is a time axis and any arbitrary variation. Now, when we are transforming this signal, we may consider the whole interval for the signal, if it is a finite signal in a discrete domain. So, we may consider that whole interval would be as a signal and apply the image the signal transforms here. It is a signal. So, transforms on this signal, for example, Fourier transform, and you may get some kind of Fourier response. Say this is a magnitude, and suppose this is the phase of the signal. Now, this is the Fourier transform representation. But suppose I want to see I want to take a sub-interval of the signal, and I would like to get what are the components are there, frequency components are there within that. Now, this information is not available from this global Fourier transform, what I should consider when we consider the whole signal together. So this is the problem of localization of the components or structures at that point in the transform domain, which are not there in the usual transforms what we discussed so far. Now, this particular aspect, they are taken care of by these wavelets, because the basis function, if you consider for the Fourier transform, you know that they are they are sinusoid of certain frequency and of varying frequency. So, when you are defining a basis function, actually you are defining the function in an infinite length of the original space, and you are taking the inner product of that functions with respect to your original, your input signal, and then that coefficients you are computing. So, in that is why the localization part is not there, because you are taking the whole interval itself. But suppose I have in some way some basis functions whose functional definition will be restricted to only within that interval, where actually we are going to study the structure. And this description can be defined as if you can define some functions like this, that means this is a function which has a finite support, like sine function it has an infinite support in time domain. But suppose I have a finitely supported functions of this interval, say this interval, say t0 and t1. So, let me define some functions like this, and then for any interval these functions could be translated or it could be dilated, which means the same functions. With these functions I can define many other family of functions where I can translate these functions at other time interval also with the similar functional variations, or I can dilate it, which means I can consider a larger interval and I can consider a dilated form or expanded form of this function. So, all different kinds of basis functions from the single basis functions we can derive, and we consider the inner product of those functions with respect to the original signal, and each one will give me the component of that basis functions within that signal within that time domain. So this is what is considered, that it should be a basis functions with finite support. Not only that, its effect in the transform domain should be also very finite. That means since we are trying to get a transforms in the transform domain also the function should have certain finite I should say finite support, and the other part should be you can have so it should have a finite support in the transform domain also. Like in sine function, we have that advantage, because then we can say that for this structure you have these are the coefficients, these are the structures. Say sine functions, you know that only with one frequency this component is there. I mean, in the complex domain, of course, you have to consider both the complex frequencies, but it has a finite, very narrow interval, so it's just impulse function at that point. So for sine function has a finite support in the frequency domain, but it does not have the finite support in the time domain. But wavelets, we would like to have that kind of functions, which we call them wavelets, that it has ideally it has a finite support in both its original domain, which could be time or space as per our context, and also in the transform domain. So usually we consider that's the frequency domain part of the frequency domain is the transform domain. So with this motivation that we should have the wavelet such basis functions, and that is how wavelets we are going to find out those wavelets. Now the problem here is that ideal, if you consider this ideal scenario, that both finite support in time and frequency, now no such functions exist which truly satisfy this. So there are various attempts to match these properties as far as possible, and which acts as basis functions, so that it has good localization property in both the domain. So some of the examples which we could consider here, say you can consider a Dirac delta functions the time domain. Now these examples once again I'm discussing in this lecture also. In previous lecture I mentioned this, so just for the sake of continuity we are repeating this part. So you have the say Dirac delta functions, and Dirac delta functions, as you know, that it is a finite support, because it is only defined within t equal to 0 only. So infinitely small interval, you can say this Dirac delta functions, and you should know that its property, though it's an infinite, it is an infinite pulse, but its energy, that means it's if I take the integration of this function, its sum of areas over that should be finite, and that is equal to 1 for an unit impulse functions, Dirac delta functions. This is a property that you have. So when we apply the Fourier transforms in the time domain, then it is a constant term in that in the time domain itself also. It is it has a constant so it has all the components. It has all the components in the time domains. So some description is wrong. So which means that it has an infinite support in the frequency domain. You consider the sine functions which I have discussed earlier. So it's an infinite support in the time domain, whereas if I take the respective Fourier transform, so since it is of a single frequency sinusoid, and that frequency we can see that it is a frequency is 4. So you will find that there are two such impulses in the in the frequency domain. Now, once again, these are some of the examples where it is not serving the purpose for being a candidate of wavelet basis functions, or for being a candidate of an wavelet itself. But there are some functions, and actually one such function which has the same form in time and frequency domain. That means whose transform is also of the same form, and in the time domain, since it has also virtually it has practically it has some finite support. In frequency domain also it has the finite support, and this function is none but this Gaussian function. So we have seen its applications in various other cases. Now in wavelets also, Gaussian function has this interesting property. So suppose this is the Gaussian functions in time domain, and this is the functional form. As you can see that this sigma is we call it basically it's a standard deviation of the functions. We'll define the standard deviations of the functions here. So effectively, this width will be a function of this sigma, and then after that the functional values are tending to 0. It is almost negligible. Now, if I take the Fourier transform of this function, it would be like this. That means this is a Fourier transform, and you can see that this is also in the form of same functional form. And if I plot these functions with varying frequencies, it would also look like a Gaussian. It is in the Gaussian curve itself. And where you may note here that now this sigma is in the numerator of its variable. So this sigma was in the denominator. So which means that this interval would be 2 by sigma here. So, so in a way you can see that though if I take narrower Gaussian pulses, that means width is small, that would spread over the frequency part, frequency domain. But again, the wider one would have the narrower one. So there with some kind of trade-off, the Gaussian functions would be used where we can say in a practical sense it has a finite support both in time and frequency domain because of this property. But there is one interesting part actually from Gaussian functions. You have observed that if I take a finite support in time domain, narrow finite support, it has actually the support in the frequency domain will be then wider. So this kind of antagonistic trade-off, that means we want finite support both, but we will have always a trade-off. So this could be explained, or this could be interpreted in terms of Heisenberg's uncertainty principle, what we have for quantum physics. So in the functional properties also, this uncertainty part can be modeled in this way about this weight, because this weight which are considered by sigma parameter here. So if I which is the standard deviation of the functions. Now if I take the variances, so product of the variances of the function in the time domain or in the original domain and correspondingly the function in the transform domain, then this will be always greater than equal to 1 by 4, which means there is a kind of inverse relationships between them, as you can see. So variance of so this variance is defined as t weighted g squared t. So if I consider, for example, it is the mean of that. So this is the definition of a variance when we have a function gt. So if I say that this function sigma g function, its variance can be defined. So it is sigma square can be defined in this way. So you can see that it is actually the definitions of the variance of any variable. So variable of t, that weighted mean of the functional domain itself. Similarly, you also define, use that definition in the frequency domain. So this is a definition here. So now let us consider that how we can design some of these wavelets by exploiting these two trade-offs. For example, you can use a time limited signal, say square pulse. Square pulse is a time limited signal, and then if I consider or you can consider a band limited signal, which means its transform domain representation is also a square pulse. You know that there exists a function. If I take the transform frequency response of a signal, this is the frequency response. It is, I am showing a magnitude. There would be phase, linear phase would be also there. So if this is the signal, then if I take the inverse Fourier transform, you will get the time domain signal. And that signal naturally, as you can understand, if it is band limited, its time domain signal would be basically of infinite support. Similarly for square pulse also. And so if I use some sinusoidal signal, I have already seen that I have already discussed that it has a very small finite support. Infinitely small actually. So to wavelet to satisfy both, what we can do, we can take these two kinds of signals and then why don't you multiply? For example, you have a square pulse. So you have a square pulse here. So for example, this is a square pulse, and in the causal systems definitions, let me take this one. And this is a sinusoidal signal. Anyway, I mean, in a functional definitions, theoretically, you can take a square pulse in both also the negative axis. And now you can take the respective multiplication of these two, right? So what you get, you get here, you get a signal. So outside, once again, since it is 0, so the product, this part would be 0, and only the variations, sinusoidal variations within the square pulse in the product, that would be felt. So this is one kind of signal. As you can see, it has the finite support in the time domain, and you can also see that its support in the frequency domain would be also practically within certain limit. So this is a candidate for wavelet. In this way, you can design a wavelet. So in the similar, and you should note here that the DC component is equal to 0 with this kind of wavelet here. So you are choosing functions in such a way. So there are using this kind of intuitive, I should say, reasoning, and we define different kinds of wavelets, and then we can exploit, we can analyze, find out its mathematical properties, apply those mathematical properties in signal analysis. So one popular wavelet family is Gabor wavelet. So where it is, we take the Gaussian signal to one that is also has a finite support, and you also take the sinusoid signal which has finite support in the frequency domain, and then you take the multiplication of this. So instead of square, if I take the Gaussian pulse, then it looks like this. So this is one kind of signal. Since it is of course complex, so it's a real part and this is a imaginary part. So they form also a candidate for wavelet. So these are the Gabor wavelets. So you can what you can see here the parameters are sigma and also frequency. Those are the parameters. They can define a family of Gabor wavelets. There is also another wavelet we call Shannon wavelet. Say you consider this function, which is the commonly called sync function. This is the name, and its definition can be found here with the standard functions which you know. Now, if I plot the sync functions, you can see that it has an infinite support. Definitely it goes, but it is tending to 0, which means practically it has a finite support. So these amplitudes are reducing, slowly reducing. So it is tending to amplitude to be 0. So after some times it is negligible. So this function, if I take, and you know that its frequency domain representation would be its frequency domain characteristics has a finite support, though it has an infinite support in the time domain, but still, as you say that practically it is it is dying down as t tends to infinity. On the other hand, if I take so this is the frequency domain representation of sinc function. So this function, as I was saying, that this function itself could be the candidate of wavelet. So we are not going to take any product, only this property, since it has practical finite support in time domain, and also its respective support in the frequency domain, which is ideally a finite support. I mean, theoretically it's a finite support. So we can take this function, sinc function, also as a wavelet function, and the parameters, by varying the parameters, say here the b is a parameter here, for example. By varying the parameters, you can get a family of wavelet basis functions. This is another very popular wavelet functions, which also has a finite support in the time domain, and it has also respective frequency domain characteristics, because you see that it's a kind of a square pulse wave, and it has that sinc property, sinc function. Its frequency domain representation will also have a sinc functions. So when we consider a wavelet's basis functions, naturally it's a set of basis functions or family of basis functions that we have to consider, and when these basis functions are all wavelets, we call it family of wavelets. Now, when we generate this family, I just mentioned in my just previously, that if I have one basis function, then from there I can generate all other by varying those parameters. So what are the things we can do? Say we can translate in the time. So these basis functions are usually defined in the time domain or in the original domain of the function. As you know that basis functions are defined in the original domain of the function. So what we can do, that we can translate these functions at regular intervals, so that we can get those localized properties of, by taking inner products, we can get localized structures of the corresponding function. And also you can dilate it. Dilate it means that, which means that when you are dilating in the time domain, actually you are localizing in the frequency domain. So you are getting also localized structure in the frequency domain support. So this is, for example, this could be a candidate wavelet, and then if I translate, these are the certain things, and if I use dilation, then you can consider you are dividing it by this time is scaled by s. So this is the effect of dilation. So you can see that this time period is now mapped, and with the same interval you get this gets expanded. This function gets expanded in the same interval, and you have more low frequency components here. So continuous, so using this family of wavelets, in the same way, the way we have computed the corresponding coefficients of the transforms, which means the forward transforms, you can see this is what is the inner product of these function and also the corresponding basis functions. This is a complex conjugate because you are taking inner product. Now, the thing is that, of course, these transformations may not be orthonormal or orthogonal. So, we are not, we cannot use that same convenience, that property. If it is orthogonal, it can be orthogonal, then you can use the same way the expansions, and its inverse transform also would be mostly similar to the forward transform. Instead of complex conjugate, use simply that function, basis functions like Ws tau, and then with this coefficient, linear combination of these coefficients of those basis functions would give back the corresponding function if it is a complete basis functions, also orthogonal. But no, it may not be so. So that's why the inverse transform. So theoretically, it is possible to reconstruct from here, though this representation we call it a redundant representation. But this is the expressions by which you can get back the signal in the original domain itself. and this is the no, definition of C-phi. So this is how the mathematical expressions that work for the inverse transform. So one of the things you should note for wavelet transform, that is one characteristics as I mentioned, in the ordinary transforms like non-wavelet transforms or whatever you discussed for example Fourier transforms, there was a single parameter. So even for it's a one-dimensional transform. So even transform space there was a single parameter like say only frequency. But when you are considering these kind of wavelet transforms, since we are trying to localize both in space and frequency, you have two parameters. One related to the space localization, which is translation parameters, another related to the frequency localizations, which is the scaling parameter. So that's why the wavelet transform will have a two-dimensional representations instead of one-dimensional representation. So this is that, and the interpretations as I mentioned that since it is translated at tau here, this is a translation. So once we compute this particular coefficient, so it is trying to see that how correlated is this wavelet function at that instance. How correlated is this? So so that is what the inner product says. So it reveals the structure of function at multiple resolution, because at that point you can vary also scale s, and which will give you multiple. So you can dilate the functions. So you can get a very small narrow you can also consider the narrower width. So when it is a narrow pulse, it has a larger support. So the structure would be in a larger interval, but when it is a wider pulse, it has a narrow support in the transform domain. So I would be discussing one particular type of representation here in much more details, which are easier to understand, and you will see its relationships with the wavelets. That is multi-resolution representation. Now, this is required for processing images, because the image what you capture, it has certain given resolution that depends upon the imaging system. But no, when we observe any particular object, our observation varies with the variation of the resolution of the. For example, the resolution means, suppose there is an object at this point, and when you are observing observing at a distance which are very close to this object, so you may not be observing the full structure of the object, that full surface, all the total surface or visible surface will not be there. So your attention will be restricted to a particular part of the object. So this is one kind of resolutions. So it is observed in a higher resolution. So, but when we are moving away from this object, your field of view is also getting wider, and the object's structures at the lower resolutions that would be revealed to you, and you will get different kinds of informations regarding the object surface, properties, color, whatever. So the resolution is very important. So when you are taking an image, it is your camera has become eye of the machine. So at that resolution, it has observed the object. But is there any possibility where we can have also interpretations as if the observer is moving away? That means by making resolution, coarse resolution, still it is trying to understand the structure. So it will be interpreting structure at those resolutions, which may be quite different than what we see at the higher resolutions. From the machine's point of view also, some of the informations related to lower resolution could be convenient to extract than if it processes at the given resolutions of the camera. So that is why there are image processing techniques or methods which require this kind of resolution, setting of the resolutions of the images depending upon its application, depending upon its requirement. So, given the image at certain resolution, it requires to transform that image to the required resolutions, what is meant for the processing. So, so every time, what we can do in that case, that if I give you an image, can we also represent a multi-resolution form, so that my processing, the machine, it cannot always ascertain that what is the appropriate resolution for its processing. But what it can do, at least, it can consider every resolution of the image, and through processing, it tries to find out whether the desired feature is available at certain resolutions. So, when you are, so instead of computing time and again multi-resolution images and processing them, rather, why don't you represent the image into this multi-resolution form and give it as an input to the machine. And that is what is the multi-resolution representation, the motivation behind the multi-resolution representation. So, one of the technique for multi-resolution representation, which is very popular, we call it Gaussian pyramid representation. So, let me explain this particular representation. So, the term pyramid, it comes because certain kind of structure we visualize for our convenience, and the term Gaussian comes actually what we do, that when you are considering a given resolution of the camera captured image, you cannot increase the resolutions, but what you can do, you can decrease the resolution. So, for that, what you have to do, you have to downsample it. You can downsample it, but before downsampling, as you know that there are higher frequency components you should remove because of this Nyquist criteria of sampling. So, before downsampling, you should filter it, and then you perform downsample. So, so that filter, what we use, that is a Gaussian filter, which is a low pass filter. We already know, we know that part. So, that is why the term Gaussian pyramid is used. Use Gaussian filter for downsampling the images to get the image at lower resolutions, and also you build up a pyramid kind of structure, where from higher resolutions you move towards more lower resolutions or coarser resolutions and represent the information in certain way. So, that I am going to explain here particularly. Suppose you have an image. So, I am intentionally showing it as if it's lying on a flat surface in a three-dimensional structure. So, suppose this is an image captured by the camera, and this is your given resolution image. So, I am just noting down the 0 by saying that it's the initial resolution of the image, and then you perform the lower resolution operation on that, the way I said that you have to perform the Gaussian filtering and then you do the downsampling. Since we are doing downsampling or resizing, say we are resizing by its size, some say half of the width and height. It could be any other factor also. So, this becomes your next level of description of the image. You could have, you might not have used the downsampling operation. Simply, you could have done this filtering, and that is your lower resolution representation. But as you know that it is sufficient because you are having low frequency component, so you do not require that you do not require that kind of high frequency sampling rate. So, data could be also reduced. So, this is a part of that compression what is required here. So, you are saving storage here in this way. So, you can downsample it. But the point is that with this representation, you are losing also information, and for a multi-resolution representation, I could have stored this one and this one. That is also one possibility. But there are a lot of redundancies in this case, because many of the redundancies we can see that this water and this water, they are quite similar. So, this redundancy is there. So, why do you repeat this kind of representations at every resolution? So, is there any efficient way to represent? And that is what Gaussian pyramid takes. What it does not represent rather this image in its original form, it will represent this image and some additional information which will be sufficient to reconstruct this original image from here. So, what it does to do that? So, it will, since it is downsampled form, it will upsample it. So, you see that it will upsample it and then take the difference from the original image and represent only that difference. So, we have I1 and we have D1, this is the difference image. So, both of them, using both of them I can get the reconstruction, because for that what I need to do, I need to say this is my detail. So, what I need to upsample I1 and then add D1, then I will get I0, right. So, in the Gaussian pyramid form, I am not only I am representing this one and actually this one, not this one, right, and you go on repeating these operations. So, like next level I will take this as your base image and I will perform these operations. So, I will get another level of representation with further lowering the resolutions, and there from this image and its detail can give me this image. So, this is I2, and again using the similar operations. So, we get this is what the difference image, we call it details, and then I2 and D2 will give me this one. Again from this and this one will give me this one. So, what I need to store, I need to represent only this image and this image. So, this is called approximation image and these are called details. Details at that resolution, these are the details at this resolution. So, in your multi-resolution representation, you need to represent only this. Now, you can do it, you can go on doing it till you reach certain level of resolutions. After that, information does not have any kind of descriptions you are not getting, or details are almost getting zero. So, you are this is how you can build up a multi-resolution representation, and the terms Gaussian pyramid comes from this. But you should note that how this information is represented. We are not storing this one, this image and this image in the computer, rather we are storing this image and this image for the Gaussian pyramid representation. So, this is the full form. If I use this one and this one, then I can reconstruct the original image in the original resolution by doing this. You can see that I have started this operation, upsample this image I2 and then add the details, which will give me I1. So, then I will upsample I1 and add the details, which will give me the original image. So, in the same way, I mean what I described, it is possible to do that. And as I mentioned that I2 is called approximation and both D and D1 they are called details. So, I am just showing it in its proper display positions. So, say this is the image, and if I took the multi-resolution representations, so I will represent this is the details and this is the approximation at this level. Again, I will proceed further approximating it. So, this is the approximation at this level and this is the details. Okay. So, while doing approximation, as I mentioned, we are doing a convolution with the Gaussian with the Gaussian function. So, since it is 2 dimension, we are doing it 2-dimensional Gaussian functions. So, that gives you one kind of wavelet functions, and so since you are doing convolution, which means this Gaussian function is translated at every point. So, it is the translation, and at multi-resolutions forms, this Gaussian functions width is going to be it will be increasing effectively they are increased, though actually since you are doing you are applying this Gaussian smoothing in the lower resolution, still this function weight remains same. But effectively, you are doing effectively this one. If I try to apply from here itself, the width of my Gaussian functions would have been larger, will be larger. So that is the dilation part. So with this approximation, you are using a family of wavelets which are the dilated and translated and dilated from this wavelet. We call it mother wavelets of the approximation. Similarly, for the differences, you are actually using difference of Gaussian. So because you have seen that now you are doing the Gaussian smoothing and then you are taking the differences. So difference of Gaussians, if I also in one dimension, if I plot it, it would look like this. This is the kind of wavelets, and these wavelets are computing the details. So this function is called scaling function, scaling wavelets for scaling function, and this function is actually called wavelet functions, which has that variations. And this is also dilating, it is also translating and dilating. So filtering and transformation is equivalent, as you know. So now we will be considering a particular type of wavelet transform which is used quite often because their computation is simple. So this is a wavelet function, as you have said, and if I consider scaling function, this is simple approximation, averaging of that particular thing. And using them, so this is the scaling functions, and you can use the translation and corresponding dilations of that. So this, and one of the thing is that these wavelet functions, from these you can generate a set of orthogonal functions. Now you don't require to use each and every wavelet functions through translations. Only a few can give you that set of orthogonal functions. So we can talk about discrete wavelet transform using this kind of wavelet functions, where you are applying on a definitely on a finite sequence, and by those functions you are translating only at discrete grid points, say this one, and then your basis functions will also have a finite number of basis functions, and they are scaled by powers of 2, say 2 to the power j. So that means you are dilating by the factor 2 at every resolutions. So this is one of the family of scaling and wavelet functions. You can see that this is that scaled part, and it would come here also. So this is how these functions are defined. So downsampling, as I mentioned, takes care of dilation of wavelets and allows to use the same function at that level. So that is the advantage. If you downsample it, then you do not require to dilate effectively. You do not require to dilate the function. You can use the same function. That would give you the effective dilations at the downsampled positions. So I will just show an example how for 8-point data, that means 8-dimensional vector, Haar wavelet transforms looks like. So you see that this is the corresponding approximate scaling function, and this is the approximation functions. But scaling functions, you are dilating it. So you get this is one kind of functions here. You can see that one kind of transformation matrix at this location. So this scaling function, it gets dilated, not dilated, translated, and similarly your these functions are also translated. But this is only at one resolution. But if I want a multi-resolution representations, then I need to do it at different scales. So that's why I have to use I can use a certain set of basis functions which captures also multi-resolution representation. So there could be different sets of orthogonal Haar wavelet functions for different resolutions and at a given resolution, or you can consider certain multi-resolution representation from there from here also you can get those representations. So I have already mentioned that these are certain factors that why downsampling and downsampling operation takes care of using the filters of the same functional same impulse response, functional form of the impulse. You do not require to scale it. You do not require to dilate it using that scaling of time domain. Now this concept particularly, because you are using the same filter repeatedly at different at different resolutions or downsampled representation of the signal. So this is effectively used in various kinds of transformations. So we consider also it's a kind of filtering banks. Say you have a band of filters. Minimally, we have two types of filters. One is for low pass filter, which is for getting the approximations. Another one is high pass filter. So this is the operation. So we are considering say two filters. So Hn is the impulse response, say it is of low pass filter. Gn is the impulse response of high pass filter. And since their bandwidth is now bandwidth becomes narrower, so say half of the bandwidth. So then you are basically downsampling them in the representation. So given xn, so finally this is approximation, this is details. Now if you downsample them, the length of xn, suppose you are downsample them by at the rate of half. That means the length here would be n by 2 and here would be say we have finite sequence of capital N. After downsampling it will be n by 2, it will be n by 2. So in a way you can see that length of your vectors still remains the same in this representation, because from there you can once again you can get back the signal if you use operation, say you upsample it and then use two filters H prime n, which may not be the same as Hn. So there is a mathematical analysis by which you can choose such combination of Hn Gn at this end, which is called actually analysis. This is the analysis end, because you are analyzing the signal to get the approximation and detailed structure, and then at this end, which is called synthesis, okay, by using a pair of filter. So you can choose these combinations in such a way that you can get exact reconstruction. So it is x prime n, but you can also get exact xn reconstruction of the signal. It could be an approximate reconstruction. Now there is a theory called quadrature mirror filter theory, and with that theory you can generate this signal. I have already mentioned this part is analysis, this part is synthesis. So this decomposition could be performed at multi stages, and there is a kind of decomposition which is called dyadic decomposition. Let me explain that. So you see that here we are not decomposing the high frequency component at each stage. We are keeping it in its form. You notice that Gaussian pyramid representation, it's a dyadic decompositions of the signal. So we follow that same thing. Only the low frequency part is getting decomposed at every end. So this is the form you can do, and then reconstruction would be also in the other way. You can also get the reconstruction. So this is approximation at these resolutions. This is approximation at this resolution. So these are the representations which are finally retained for representing the signal. And while reconstructing, once again you can use synthesis filter for reconstructing this resolution XA1, and then once again another synthesis filter for reconstructing Xn. Now since you are using same pair of Hn Gn, your synthesis filter bank also remains the same. That is the advantage. So these are certain tricks, I should say, or good techniques which are used in getting wavelet transforms. So as you can see, at each level sample size is up, so equivalent of scaling by 2. So total number of samples still remains the same. I mentioned that. So some of the typical wavelet filters that we may consider, I am just giving you two examples. One is Daveshi's 9x7 filters. Now, Daveshi has given, Daveshi is a very renowned, scientist and did pioneering work. She did pioneering work for wavelet analysis and synthesis. And with the theory, what she has, what she has presented, with that theory, you can design a various set of filters using that. It has the property of quadrature mirror filter, that property. So, this filter bank, these are the analysis. This is one typical example, 9x7. The term comes because you see that this low pass filter length is 9. There are 9 samples. Okay, there are 9 samples, both 0. So it is centered at 0, and it has sequence has both negative and positive time domain, time axis. And whereas your synthesis filter is of length 7. You should note there is a shift which has been shown here just for the sake of, from the analysis it has come. And this is the similarly the synthesis part, the low pass filter is of length 7 and the high pass filter is of length 9. So if I use that, then I can use this one. And there is another filter that is legal. Again, legal also is a researcher who has proposed these filters, and there these are 5x3 filters. So you can see that low pass filter is of length L and high pass filter is length 3. So this is 3. The one of the interesting part you can find at the legal filters. Now these weights are such that you can use integer arithmetic to compute this filtered response, because this is one of the advantage of legal filter. So when you talk about once again two-dimensional transforms for the wavelets, say it's the same feature or same properties of the functions what we have used, like separable property, that makes this transforms convenient in 2 dimension. Extension becomes convenient. So you can again think about separable filters. So your basis mother wavelets, they get simply multiplied in both the domains. They generate 2-dimensional mother wavelets. So and there also, if I consider the transformations here by this 1-dimensional sequence transformations, the same thing we can do. We can repeat the similar computational model where the 2-dimensional input could be considered as a series of rows and series of columns. So we can transform columns and then rows or vice versa, the way you interpret it. So with this, let me give one example. Say this is the original image, and if I perform the 5x3 analysis filters, first in rows and then in columns. So you will find that there are, I have used the 4 components. So this is the approximation part and these are the details. This is one level of decomposition. In the next level, once again I can decompose it also in 4 components, where this will be the approximation, these will be the details. Now while doing these things, I have used the 5x3 analysis filters. So while reconstruction, I can use synthesis filter to reconstruct back the whole signal. So these are the high frequency components at this resolution, as you can see, and this is the low frequency components. And the directions, it shows that it is not simple high frequency, low frequency. I can say both are low frequency, both directions we are applying low frequency filter. But in this case, since I am transforming rows, so it is basically high frequency for row and low frequency for column. In this case, it is low frequency for row and high frequency for column, and here both are at high frequency. So these are the components. We denote sometimes this component as low, low, high, low, low, high, high, high components of this image using wavelet transform in these resolutions. And you can repeat this process so that this image you can have low, low component, high, low, low, high, and high, high component here also. and you can process, you can proceed at multiple resolutions. So this is how wavelets are used for this. Wavelet transforms are there. So there are various applications like compression. You can use denoising, because most of the noise is noisy part would be in the high frequency part. So you can set those coefficients to 0 and reconstruct, then it is a denoising part. You can use feature representation, because you are computing at certain localized properties of the signal. Those structures can give you the feature representation. Or image fusion you can use, because as you can see that it is it is separated into several bands. So you can fuse those bands appropriately and get a appropriate image, fusion image. So there are various such applications, you can note it down. So with this, we come to the end of our discussion on image transforms. So just to summarize that what we have discussed, as I have said, that alternative representation, it provides other insights of structure of images, and low frequency and high frequency components, both are they would be there in the structures. It may become useful for providing more compact representation. Only a few transform coefficients could be sufficient sometimes to represent the whole, either the signal or image. And this is what is used in various compression standards, because our perception, using the human perceptions, perceptual behavior of certain components at certain frequency components, if we can have a model, so we can selectively quantize those coefficients. And from the perception point of view, we can get almost similar kind of perceptions of the signal. So the image compression used this kind of selective quantizations. Sometimes they are convenient for processing. I just mentioned that because you are decomposing into several frequency components, and then you can perform, say, filtering or enhancement. Those are very convenient in transform domain operations. Also, we have seen some of these operations. Regarding wavelets, you have certain special mentions here, as wavelets provide some redundant representation, but it is very useful for processing for various reasons. So one of the things is that it represents the scales of features in an image as well as their positions. So multi-resolution property of wavelet transform, that is mostly used and very unique, corresponding to other kind of transforms. So it has both time scale and space scale representations, and computation is also fast. The computations with the filters, convolutions can be carried out, use fast methods. So we have a fast forward and inverse transform. It provides multi-resolution representation. Once again, it has emphasized this part. Like this, is useful for progressive and scalable processing of images. And using wavelet transformation, both lossy and lossless reconstruction possible, because you can have certain finite set of coefficients and you can get full reconstruction. So useful for a number of applications, including image compression. And you know that like JPEG is the standard for DCT based compression, but for wavelets in JPEG 2000, it uses wavelets for its transforms. So with this, let me stop here, and we will continue our discussions on other topics. Thank you very much for your listening.